Great. So before I start, just a quick little public service announcement. I think both in the printed schedule and outside, the title of the session has been User Dependency Injection. I'm actually, in fact, going to be talking about using dependency injection. If you've come to hear about the former, sorry to disappoint, you're in the wrong room. But maybe at the end you can come and talk to me because I am interested to know what you might think user dependency injection is. In any case, my name is Eric Chang. I'm the technology lead of the data services team at Opower. We build code infrastructure on top of Hadoop and HBase, but we're also practitioners, and we're solving the problems of Opower's customers. And these are pretty interesting problems that I'll talk about a little later on the slides. So as practitioners, we use the tools that are available to us and to solve those problems. And historically, some of those tools have included dependency injection. Now, I know dependency injection isn't really a mainline topic at Hadoop Summit, but it's a well-established approach. And my goal for this talk is to convince you that what's old can be new again when applied in the context of your Hadoop infrastructure. So just a quick agenda. I'm going to cover the problem statement. I'm going to talk about the solution in general, give an illustrative example, talk about how Opower has applied the solution in production to serve products to our customers, and then we'll wrap up. So let's talk about the problem statement. So Hadoop is hard. Well, obviously, I'm being a little bit tongue-in-cheek here, but I'm trying to make a broader point, which is that we should be concerned, we should focus or think about a separation of concerns as we build our code. And so relying on that principle, I'm going to make the bold claim that there are going to be parts of your code base that don't actually care about Hadoop. And so for those parts of your code, Hadoop should be hard, right? Or should be not my concern or just entirely invisible. The most salient example of this, and really the reason the talk is titled the way it is core application logic, core business logic, whose focus should not be about Hadoop plumbing. It should really be focused on solving the problems of your customers, right? So the challenge that we're posed with is, how do we build an effective separation of concerns and deploy Hadoop-agnostic code into our cluster? So let's dive a little deeper into that. Why do I care about separation of concerns? So there are definitely going to be a lot of Hadoop deployments that are purely greenfield, brand new code, and we have some of that. If you're in that class, that's great. But you might find yourself in a position similar to ours, where you have to migrate existing code components to your Hadoop infrastructure. And irrespective, really, of whether you're dealing with new code or existing code bases, separation of concerns it gives you, via good code componentization, enables you to reuse that code in interesting ways. And I'm going to show what that means later on. The other thing about keeping your code sort of blissfully ignorant of Hadoop or MapReduce, for example, it really allows you to have a little more focus within your organization, right? You can have some developers who are entirely focused on Hadoop plumbing and infrastructure and understanding how to partition and move your data. And then you can have another set of customers who they're really domain experts, right? They know how to solve the complex business problems and in isolation of the Hadoop infrastructure. And the last part here is that there are testing frameworks, like MRUnit, but by definition, if you test at the map and reduce boundaries, that's pretty coarse-grained testing, right? So code componentization lends itself pretty well to more granular and as well as lighter weight testing. So that's why we should have separation of concerns. Hadoop doesn't really do it, right? Serialization, input-output formats, partitioning, those sort of bits of Hadoop are not really portable. And it doesn't provide a lot of guidance out of the box in terms of how you integrate existing code components. So let's go ahead and jump to the solution. As is no surprise, dependency injection provides a solution for us. It provides a means by which we can have application logic that doesn't explicitly configure its dependencies, but instead interacts with interfaces. And the implementations of these interfaces are managed by an inversion of control container such as Google Juice or Spring Framework that we use. And then your main application assembles the appropriate implementations of these interfaces into your container, asks for the interface that it wants to interact with, and it invokes the business code on that particular piece of logic. So even if you're already familiar with dependency injection, or DI for short, these next two slides will help lay the groundwork for the rest of this talk. So let's start by illustrating the use of code components in the traditional real-time pattern, and then we'll show how we can apply that to Hadoop. So we'll start with our application logic. It's sitting in the lower right-hand corner here. We have an interface, that's the business service interface, sort of generically describing that. There's a single implementation out there that is the implementation of that business interface. It interacts with a read DAO, and DAO is shorthand for data access object. That's a pattern that allows you to encapsulate your data store. And it also, it interacts with that read DAO to extract objects, right? The things, the domain objects that your business cares about. It then interacts with a write DAO to write those objects back. This is a sort of artificial bifurcation. I wouldn't normally split up my DAOs into reads and writes, but it's illustrated for this example. So the service and the DAOs are all managed by this inversion of control container. In this case, we're talking about a real-time context, right? So what we want to provide is implementations of these interfaces that are going to serve our purposes. So in this case, I have both a real-time and a read and write DAOs that are going to be backed by a data store. So that could be HBase, for example. If we're in this real-time context, there's somehow someone is asking for this data. So let's imagine we're in a servlet container. An end user hits your website. You go through the container stack. At some point, there's a method, a real-time call from the web. It asks for the business service from the container and calls run, right? Okay, so, oops. So as you can see, dependency injection allows the calling code to interact with interfaces instead of concrete implementations, and we'll see how this works to our advantage in the next slide. So same code. Now let's say you're executing within a MapReduce job, right? Everything's the same in the container, but let's take a look at the arguments that are provided to reduce method. If you think about keys and values, those really form your data source, right? That's where you're getting your data from in your MapReduce job. And your context is your sink, right? That's your table output format, your text output format, et cetera. So using those generalizations, in this case, we're going to take the values and keys and put them within a read DAO. We're going to take the context and inject that, sort of wrap that around in a write DAO, provide both of those to the container, ask for that same business service, and then call the business method. So this business service on the right-hand side, nothing has changed, right? It doesn't know that it's in Hadoop versus real-time. Everything is the same here. Just to dig a little bit deeper in here, the reason that this works is because we've got, in this case, we're going to actually use a short-lived IOC container. Because if you think about the real-time case, my real-time read and write DAOs are backed by a persistent store such as HBase. That store doesn't go away. If I'm thinking about in this case, I'm calling a method, right? And each invocation of reduce is going to have a different set of keys and values. So the way that I address this is we have sort of an ephemeral container we spin up for the scope of this method, inject the values as we need to, and then shut down that context after we're done each invocation. All right, so let's jump into the example. So to more concretely demonstrate how dependency injection can help you with Hadoop, we're going to take the traditional WordCount example and flip it on its head. So I'm going to follow the recent Hollywood trends, and I'm going to tell the WordCount origin story, right? So there was a time before WordCount was a massively parallel petabyte scale example of how to use Hadoop. And in case you're not familiar with WordCount, that's fine. Just imagine there was a time when people used to count words one at a time in small artisanal batches. So as the disclaimer says, it's kind of contrived, but useful for the sake of this illustration. All right, just tell a quick narrative here. So you live in New York City, you've got a beard, you built a great business around counting words in small artisanal batches in linear time. Customers and process them, again, one at a time, small batches, using your really elegant, simple code. You had a little bit of insight, though, and you knew you had to scale up at some point. So you componentize your code, as we'll see in the next slide. So let's look at the way the code's been decomposed, starting with a domain-specific transfer object. You see here the WordCount DTO. DTO, data transfer object, is just another pattern to allow you to decouple your business object from the underlying details of how it's persisted and how it's physically stored, right? So we're really only concerned with two things in this transfer object, the word and the number of times it occurs. So the core application logic, from an interface perspective, is encapsulated in the word count service. And it has a method, single method, counts a word, right? In this particular example, and in both cases, both this and the next case I'll show you, there's only one implementation of this, right? This is the pure business logic that we're going to show doesn't need to change across different contexts. What does it do? Well, it interacts with another data access object to get words, right? Then counts the words and creates these word count DTOs, and it then writes those words back through that DAO. And again, these are all interfaces, so at least so far. What we'll see is that in this particular case, we've got this is our artisanal small batch, right? So the artisanal word count DAO implementation is actually going to be, pretty straightforward. We're going to open up the input file provided by the customer. We're going to scan the file in its entirety. Every time get words is called, we're going to return all the words. And maybe we'll be a little smart in cache, but the whole idea is that this is all linear, right? We're going to go through the file every single time. And that's OK, because it's handcrafted, we're small batch. That works for us. So here's some code, core business logic here. This is the implementation that I talked about. It interacts with these interfaces. You can see in bold the word count DAO is where it gets its its words from. For every word that is returned, if that matches the word that was provided to this method, it increments the count. It then creates a transfer object that includes that word in its count and then stores it back through the word count DAO. This shows how everything goes together. Don't worry if you're not familiar with Google Juice. The real takeaways here is that we're binding interfaces to implementations, right? And in this case, what I'm describing here is we're always going to bind the word count service interface to the word count service implementation you just saw. So that's constant. Every time you ask for a word count service, you're always going to get the same implementation. What this allows for, though, is in the second bind here, we can vary the word count DAO implementation that's returned, and we'll see how that goes together. So so this is how it all goes together. This is your main method, right? We create the word count DAO, get to Aspire customer. We also have a file where we're going to write the results. We construct a juice module with that DAO, and then we go ahead and ask for that service out of that module, that inversion of control container, and we count words, right? I have this kind of hand-wavy get words to count method, but assume that somehow command line or through another input file, someone is telling us what words we want to look for, right? I want to see all instances of the word cat in the input file I've given you. OK. So I'm going to go back to my illustration again. You're going to see this a lot in this presentation. Right-hand side, here's a container. I have my service with its only implementation. It's interacting with a word count DAO whose implementation is yet to be determined. In this case, we're talking about the artisanal implementation, so we wire that in. That implementation, again, is reading a file, one at a time. Every time get word is called, it's going to scan through that file linearly and return words. I have some single-threaded, main application that's calling artisanal word count. It's going to ask for the word count service through this container, and it's going to, for example, say count the word hat and tell me how many times that shows up. So if we can go ahead and press play on this video, I'm just showing you here great. Thank you. I'm just showing you the input format for those of you who are familiar with word count. This is the same format. It's one word per line. I'm then going to go ahead and run my main application. And the output should be another text file whose format is the word and the number of occurrences in the file. OK, great. So let's fast forward a bit and imagine that your artisanal days are over, and now you have customers who want petabytes of words counted. And linear time is just not going to cut it anymore. So it just so happens that your boss used to work at Yahoo, and he suggests you look into Hadoop. So you do a little study on MapReduce, you figure out how to partition your words in a map phase, and you come up with the classic word count reduce method that you see here. You build a implementation of a DAO that's going to fulfill the word count DAO contract that we'll see in a bit, and it's going to take word count DTOs and write them to, in this case, a text output format. So how does dependency injection give us the best of both worlds and allow us to keep our small batch, artisanal code root? Start by partitioning our files by word and emitting a count for each word. So this is all classic word count here, right? So at this point in the reduce method, we're still classic word count. Here's where we fork a bit. So let's go back and revisit the principles of data sources and sinks, right? Key is the word, value is an iterable of the occurrences of that word, and context is our output format. So we're going to wire that up in a DAO that is both going to manage reads and writes. We're going to wire that DAO into the container, and we're going to call the exact same method that we did in our sort of artisanal, single-threaded version. So the big takeaway again here is that there's nothing that changes within that container on the right-hand side. The word count service implementation hasn't changed, even though now it's being executed within a MapReduce context. So see how it's all wired together. This is, again, the wiring code. We're in the reduce method. We construct the DAO itself with the key values and context. We construct the inversion of control container with that DAO we just created. We ask for the word count service, and we count the word. And this time we know what we're looking for because it's provided as the key argument to this method. So I've got another video here, if we could just hit play on that. Same input. Again, imagine it's petabytes of this. I'm going to go ahead and run my MapReduce job. It's going to be a local JVM execution. And we'll take a look at the output. Output format should be exactly the same, word and a number of occurrences of that word. And I'm going to show you that that's also the same as what we got in our artisanal example, right? So same inputs, same outputs, obviously different workflows, but same core code running in both cases. So let's talk about the Opower application of this design pattern. So what does Opower do? Well, briefly, we help people save energy. And the way we do that is we work with utility companies to analyze energy usage and provide insights that are actionable. And one of the ways we do this is through a product that's called bill projection. So how does bill projection work? So we get usage from utility companies, and that comes in the form of if it's electricity, it's going to be kilowatts. If it's gas, it's therms. We then apply an algorithm which takes that usage, we figure out what your current bill period is, and we project that usage out to the end of the bill period. We have an existing code component that takes utility rate information. So how much are you paying per kilowatt of energy, per therm of energy usage, and takes rates from utility companies and applies that to the usage we just projected, right? So we have usage that we forecasted. We then apply rates to that usage to come up with a notion of what we think your bill may be by the end of the current bill period. What I'm showing here is one rendering of that. We actually serve it out on multiple channels. This is how it looks on the web. If you're a PG customer, you actually can see this today. If you go to my usage and then my dashboard, you'll see this on the upper right-hand side. This is telling me that as of today, or as of last month, I'm going to use about $30 worth of energy. And so I can act on that, right? That's high for me. In this case, I'm actually saving money, so I feel good about myself. That's good. So the one thing I do want to call to your attention is this thing in the middle, the rate engine. This existed before we had Hadoop integrated into the Opower platform. And it's decently complex. It's got a set of components that are ready in use before it was used within a MapReduce context or anything like that. And we wanted to be able to preserve that existing functionality. Outside of Hadoop, inside of Hadoop, we want to be able to reuse it. So the question is, how do we maintain this existing cases as well as apply the same code in a Hadoop environment. So dependency injection is going to let us employ the same code components in batch and in real time, and this is that reuse that we get from that separation of concerns. So we can use the same code base in batch workflows. So we tend, our push channels are going to tend to be batch. If we're going to send a bunch of emails or SMS messages or interactive voice response, if we're going to actually call people, it tends to be batch workflows. If it's a web request that the results of which you just saw on the previous slide, that tends to be an in-process calculation we want to do in real time. So depending on the channel, we can decide which workflow we want to use. The other thing to highlight here is that with this code componentization, we also have a good testing story, right? So because the code components are platform agnostic, because we can inject whatever data sources and data sinks that we want, we can provide curated test inputs, and then we can also assert results that are posted to the data sinks. So this allows us to do, obviously componentization allows us to do, nice unit testing, but from an integration testing perspective, we also kind of have a bimodal approach. We can have fine-grained tests that use curated data inputs and outputs in a real-time context, and then if we want to kind of just, gut check that data is flowing through our MapReduce context, we can do that as well, right? We can say, let me go ahead and turn on inject the MapReduce implementations and make sure that data is flowing through the pipeline in the way that I expect it to. So another illustration. So the entry point into our bill projection calculations is the bill forecast service, always on the lower right-hand side. It's interacting with the rate engine that I just spoke of. That's our kind of existing code base. Both of these services talk to a usage DAO, so another data access object, to get usage, right? The therms or the kilowatts that you're consuming. So we happen to use Spring. That's all managed with the Spring version of control container. And our usage is actually stored in HBase. So our process in batch starts with a map over that usage. We then reduce it and group it roughly by customer. And going back to our notion of data sources and sinks, we create a usage DAO, which is constructed with keys and values, which is then injected into our container. What I'm not showing here is there actually, where's the data sink? Well, there actually is another DAO that writes to the context. And that's in this case, we're actually writing a table output format back to HBase. But for brevity, I kept it out of this illustration. So again, our application logic in the lower right-hand side, the bill forecast service, it doesn't change. It's in this case a MapReduce context. And more importantly, the rate engine didn't change, right? It used to get usage. Actually, before all this, it actually used to get usage from MySQL. Now it gets usage from HBase, but it doesn't know that. It doesn't know that it's getting it in a MapReduce context. To follow the rest of this through, in the reduce phase, we go ahead and invoke the container, get the service, and call the forecast method, the core business method that we're concerned with. So that's batch. But depending on the scale of the utility company and the frequency with which we want to update bill projections, we also support real-time calculations. So in this case, everything stays the same on the right-hand side. We have our real-time requests that comes through, our servlet container. We call the calculate bill projection. Now, this is for a very specific user, right? In this case, instead of, we have a HBase back DAO, which is back directly by HBase, reading directly from HBase in a random access pattern. We invoke our container, call the service, call the forecast method, right? So again, nothing changed on the right-hand side. Bill forecast service still runs the same way it did before. Rate engine is the same way it ran before, but now we're in a real-time context. So benefits of a dependency injection solution. We're able to use the pre-Hadoop rate engine code components. The calculations can be applied in batch or in real time, right? We get to decide. And we're able to, we have a good test coverage and a good testing story around that. So wrapping up. So what does dependency injection in Hadoop give you? It gives you separation of concerns. it allows you, because of code reuse, to, as I just showed, be able to perform the same calculations in batch and in real time. There's some limitations. It does require that your code is sufficiently componentized. It does assume that your domain classes can kind of survive the partitioning of MapReduce. And it's still, somebody still has to know MapReduce. This is not a turnkey solution. This is about separating concerns, right? I mentioned having MapReduce developers and then people who focus on your domain. So I also talked about how we employ Hadoop and dependency injection to serve up build projections, and you do that both in real time and in batch. So I'm hoping that for those of you who find yourself in a situation similar to ours, that I've been able to provide a few insights and maybe given you another approach to consider as you face the same challenge that we do of taking something that's successful, it's working, right, and deploy it at even larger scale. That wraps it up. I've got the source code to the word count example posted here in case you're curious, and appreciate your time. Got some time for questions. If people want to step up to the mic, that'd be great.
I have a question. So I was wondering, how did you build the context, the IOC in MapReduce? How did you bring up the Spring?
Sure, that's a good question. Right, because there isn't a pattern right now in the Spring framework for constructing a container. So we follow a pattern where most of our beans are singletons. And so because of that, we can take advantage of the life cycle of a MapReduce job. So in the setup, we kind of create a master IOC container that has all the common components that we know we need to use. Then when we're in the reduce method, right, that's where we need to kind of bring in the runtime values, right? So there's going to be, so for example, when I need to read data from usage, that's not available in the setup method. That's only available on a per reduce basis, right? So what I do is in that reduce method, I actually construct, in Spring, you can construct a context with a parent context. The parent context is the one I created in the setup, right? And I create a new, smaller context that just contains the information I need for that invocation. So it has the DAO that wraps the values that are provided to that reduce invocation, constructs a Spring context around that, which inherits from the larger parent context. So, sure. Okay.
So how did the performance of that work? That there are some penalties of building the context. Rather than just when you start, did it add it to the overhead just without having the, let's say, the inversion of control?
So are you saying the performance with regards to spinning up an inversion of control container?
Yeah.
We did have to tune that. You have to be, particularly in Spring, you have to be careful which context you bring. So we have that on each reduce method. We definitely had to be very careful about only overriding the parts that we wanted to override. But I took some general measurements on it, and we were able to tune it where the overhead of bringing up that new Spring context was on the order of single milliseconds, so sub 10 millisecond range. Because all you're doing is creating, effectively, if you think about it, you're just creating new objects to wrap those keys and values coming in, right? So as long as you're just doing that and not, bringing in some other context which bootstraps a bunch of other services that you don't need or you already have created, you can keep it down to a minimum.
Yeah. So, okay. So you only do these small objects. So when you instantiate it just. Do you really need to create a new context for that, or you can create this DAO on the fly?
You could create the DAO on the fly. I mean, it's more of the artifact of the way that Spring wants to manage things. So in our case, it made more sense because we weren't. It's not parameter passing, right? You're not saying here's a new DAO and construct the service with it, right? The service has to be injected with it.
So you wanted to auto-wire it in the
That's right.
in the context.
That's
yeah.
right. That's right.
Okay.
Yeah, because again, we want to be able to use that code in the MapReduce and in a real-time context.
Yeah,
in
yeah.
a real-time context, no one's creating that DAL for you. That's supposed to be created kind of statically, right? So we need to basically kind of get under the hood and provide that DAL to the business service.
Okay. Yeah. That's very useful. Thank you.
Sure. All right. Thanks again.